Hi there, how's it going? This video, I'm going to be talking a little bit about just good old regular Newtonian gravity. Um, if any of you know a little bit about me or know me, um, you probably know that I have this strange obsession with a hypothesis of gravitational absorption, um, which finds its roots. Well, hell, I don't know how far back, but there's definitely some history in the early 20th century, which is pretty interesting. You can find in the history of astronomy that there were lunar fluctuations, secular accelerations perhaps they may have been called, in the late 1700s and in the 1800s. Newton said the moon was the only problem that ever made his head ache, and it's just interesting that his theory of gravity would work so well, but the celestial body which was closest to us was the one that was the hardest one to, and the one that we could see the best was the one that was most difficult in explaining with the theory. And basically 100 years after the Principia was published, the mathematicians of the time, Simon Pierre de Laplace, particularly, had thought they had finally figured out, and understood the last of the problems with the moon gravitationally, but most people agree, even at that time, and still today, there are still problems with the moon which technically don't have a true gravitational explanation. And as late as the 1910s and 1920s, certain scientists or theoretical scientists were talking about what it would mean if perhaps there was a slight gravitational absorption during a lunar eclipse. So, like, the sun exerts its gravity on both the sun and the moon. And they said, what would happen if, when the Earth was between the sun and the moon, the sun's gravity upon the moon was slightly weakened or slightly absorbed by the Earth? And so they tried to figure out what the moon's orbit would have to look like if that happened. And it actually was a striking connection, that the correlation. They saw that for a couple of years, or maybe a few years, some physicists or theoretical scientists actually thought that had to be happening. They thought there was a slight gravitational absorption because it matched up with the observations, the real orbit of the moon. But the match was not perfect, and eventually the idea kind of fell by the wayside. But it definitely should not be forgotten. I think it still might be useful to us today. But in any case, I just think it's interesting to go back and maybe practice a little bit with just the traditional Newtonian stuff, kind of with with those curiosities in mind. And one of the first questions I asked myself was, well, how strong is the sun's gravity upon the moon as compared to the Earth's gravity upon the moon? And if I remember correctly, the ratio that I came up with when I first tried to do a very basic calculation was about 7-4. The sun's gravity on the moon, and by that I mean the strength with which the sun pulls upon the moon is stronger than the strength with which the Earth pulls upon the moon, by a ratio of about 7-4. Now, I don't know what kind of numbers I've plugged in there, but I think if the book from Isaac Asimov, which I have, if he was more accurate than I was at that time, and since I've repeated the calculations with so the numbers that I got from Wikipedia more recently, it seems like he was closer. Although he still seems to have been higher than what I can get using the numbers on Wikipedia. But he said the ratio was, oh, I'm sorry, the ratio was not higher, but it was close. If you turn the ratio around, it would have, Asimov's would have been higher. If you say what fraction of the sun's gravitation the Earth's gravitation reproduces, his number was 0.46. So measured against the sun's gravitation on the moon, you say, what's the Earth's gravitation on the moon? And he says, well, it's 0.46 of that. And apparently I seem to be getting 0.42 or something pretty close. But it's just an interesting exercise, and I might make a few more videos here to show some of the calculations which I've made. Okay, I'm back. Let me just say that the value that I got for the Earth's gravitation upon the moon compared to the sun's was closer to Asimov's than I said. Asimov's was 0.46, and this is in the book On Time and Space and Other Things, or whatever it's called. So his fraction was 0.46, but mine, I said it was 0.42, but I got 0.452, so pretty close to 0.46. And I'll just show some numbers that I used, which I just got from Wikipedia. Okay. Here is the Earth's mass, 5.97219 times 10 to the 24th kilograms. But actually I rounded that to rounded it to I don't know how you write a symbol for, if anything, I rounded it down, not up. What kind of symbol is that? I just rounded it to 5.97 times 10 to the 24th kilograms. And first I actually compared the strength of the sun's gravity upon a human body at the Earth's surface, and the Earth's gravity upon a human body. But maybe I'll come back to that later. Instead, let's look at the Earth and Sun upon the Moon, as I was speaking before. And so the distance, or I'm sorry, the mass, for the mass of the Moon, I was using 7.35 times 10 to the 22 kilograms. And like I said, I don't know, maybe Wikipedia gave a few more numbers after the decimal point. But anyway, that was the value that I was using. And the distance between these two, I don't know, average distance, or maybe it was the semi-major axis of the Moon's orbit, perhaps. But I used the value 3.844 times 10 to the 8th meters. Okay. And so the equation, which I wrote out, and because we're comparing two different gravitational equations, I just conveniently dropped out the gravitational constant in each equation. So all I had was m1 times m2 over the distance squared. So 5.97 times 10 to the 24th times 7.35 times 10 to the 22 over 3.844 times 10 to the 8th, and that whole thing squared. And so this is the gravitational force between the Earth and the Moon. And what I got was about roughly 2.97 times 10 to the 30th, and oh gosh, I don't know if that would be newtons, or I don't know if there's any units there, but all I'm doing is comparing that number to the number that I'm going to get for the gravitation between the Sun and the Moon, which, and for that I've used 2 times 10 to the 30th, which is the rough estimate for the mass of the Sun times the mass of the Moon, 7.35 again, times 10 to the 22. And the distance here is 1.496 roughly times 10 to the 11th meters. And you got to square that whole thing. And from that I got 6.57. Sorry, that's a roughly 6.57 times 10 to the 30th. So you see the 10 to the 30ths are the same, and so we just take the ratio of 2.97 to 6.57, and like I said, that was about 0.452. So very close to Asimov's 0.46. So very fascinating that the sun's gravitation is very strong from very great distance. Yeah, I guess I'll take a break here. Maybe I'll come back and talk about that comparison between the sun and the earth upon an actual human body at the surface of the earth. And of course, the comparison's the same, whatever kind of body. You could be talking about an elephant or an ant. The ratio, the comparison will be the same as long as you're talking about the same spot in space. Alright, anyway, take a break. Hopefully I'll see you again. I'd also like to add, I realize that some of the calculations I made were pretty crude and just very basic. If you're trying to do these calculations, I think you probably want to keep track of significant figures and everything and try to however many significant figures you're using for the value of the Earth's mass, you probably want to use the same for the value of the sun's mass, etc., etc. Well, just ask Sisyphus, because he really knows how heavy everything is.